Oops, wrong class. So here we go. So what we do is we would take a cable, we would take the tension would be equal to a constant, 0.008 times what's in, and then the KC mil, right? So let's say I was going to pull a cable that contained 20, write this down. I was trying to pull a cable that required 20 14 gauge conductor. So y'all got those calculators? First of all, we need the what? We need the KC mils for a 20 gauge conductor. I think I've got that, by the way, to help you out a little bit, I think I've got the KC mils. I think I got another, I think. Let me look real quick. I think I put another American wire gauge up there that has the KC mils on it. If not, I'll do that. And that way you won't have to calculate them all the time. But how do you calculate KC mils? All you do is look up on your American wire gauge, look at the diameter and do what? Square it, right? Okay? Yeah. Pretty good sized wire, but and 20 conductors of 14 gauge wire. No, I don't have it up there. It's real easy to calculate. So what would the KC mil be for 14 gauge wire? Really? I didn't think it'd be that high. I mean, it might be. And that's squared? So we take, what? 0.008, multiply that times 20, multiply that times 0.004, which I'm taking for granted Chase is right. Does everybody agree with that? The KC mils for 14 gauge wire. Huh? Oh, you're going to do one of these on the next test, by the way, but I'm going to give you this formula. So it's up to you to understand what N stands for, and then of course KCM is the circular mil, right? I can't remember what the CMA is. Oh, okay. This is without multiplying it times 1,000. So that still wouldn't be quite right. I need to look that formula up. So what did we get up our pounds would be? Anybody got it yet? Anybody else verified that the KCM is 0.004? That's what you got. Is that what you got, Abram? 20. Huh? Pounds. I should have my calculator down here on the bottom. On the what down. There we go. So we'd take what, 0.008, right? We'd multiply that times 20. Then we'd multiply that times, what's the diameter? No, what's the actual diameter? Oh, it's stuck it in there. That's what I came up with. That's not right. Undoubtedly, it went in my calculator wrong. 0.008 times 40 times 0.004. I need to go back and check that. That don't look right. I did multiply it times 20. I'll go back and check that because that don't look right. That's less than a pound. And there's got to be something else in the formula that I'm leaving out. So let me go back. I'll go back and check that and see exactly what it is. So here, this is what I need to check. This one right here. This one right here is probably more correct because it relates to the watt. You know, see, let me find it again. So the second one seems more correct. I need to go back and check this because this is probably not. This is the watt. This is the outside diameter of the cable. So I'll go back and check that and see exactly what it is. I know there's one of them on the test, so I need to figure that. Bending radius, are we okay? Did we talk about bending radius? So a lot of cables find the bending radius. This is extremely important when we start pulling when we start dealing with fiber optic cable. The problem we have with regular cable is when we start bending a curve on the cable, then we set up a thing called an inductor, right? You understand, which starts giving us problems. And this is where we left off. We did talk about the bending radius. So bending radius is the radius of an arc of a quarter turn of a conductor, right? And if we put a center point, then this would be what we want to maintain if that's specified in the cable, right? The next thing, before we start looking at termination, let me bring up another PowerPoint slide to explain what we deal with communication cables. So when video we looked at, they said electrical conductors are used for 3 different things. What are the 3 different things? Yeah. Or both. Okay, and that's the 3 things. So cables or conductors are used for 3 things. We can send power on them, strictly power, or we can send information, or we can send both. The perfect example, if you still have a regular telephone in your house, that telephone needs to be powered up, right? You understand? When you look at the wires coming into your phone, the only ones that there's a 4-wire conductor, but only 2 of them is used, and that's the green and the red. And yet you're talking over those wires, and yet those wires do what? They power the phone up, right? So that's a perfect example if you still have a regular phone. So we actually do that on our communication system. Ethernet, the white cables up here you see, those have 8 conductors in there. Only 4 are used. 2 pairs are actually used in communication, which gives us the option of splitting it up and doing some things with it. But one of the things they do here at the college is they send power to do what? To power the phones. So our phones are powered through the cable. But they're not using the same set of wires, so that wasn't a good example. First thing we need to look at is something that we refer to as impedance matching. Before we can even have an idea of communication cables and why things are done the way they are. So review, we know Ohm's law, right? So Ohm's law says that V is equal to I times the amount of opposition in the circuit. I is equal to the amount of voltage applied to the circuit divided by the opposition. And then R is equal to V over I. When we start calculating power, we know that power is equal to V times I. It's equal to I squared times ohms, or equal to V squared over ohms. And this is what we call apparent power, which we don't get much into this class. And it won't make that much a difference as far as looking at the power transfer in a cable. And then if you, true power would be equal to apparent power by something called the power factor. But these are okay. It's just that in AC, we have to understand this is the type of power called apparent power. Conductors are used to deliver power, communication, or both, similar to power delivery systems. Electrically sending information requires at least 2 conductors, right? Now understand that. In DC, the opposition to current flow is set by the resistance of the source and the return conductors along the load. In AC circuits, the opposition is set by something called resistance and reactance. So what is the difference between resistance and reactance? We need to understand that in this class, even though we don't teach it in a lot of detail. Now, reactance varies with frequency and resistance. Impedance is a term that we use to talk about the opposition in the AC circuit. We say AC, but AC means it's just current that's changing direction. It does not have to be at a constant rate. Power is sent at a constant rate, right? You understand that. But AC signals, like my voice right now, if I was to take a microphone and look at it and then look at my voice, I'm sending AC, but it's not at a constant rate, right? It's varying with the actual frequencies of my voice. I'll try to find my cable. I got one out in my car. I think we can actually look at audio, which is pretty interesting. So impedance is a term that we use in AC that contains both resistance and reactance. And this becomes very important in communication systems. In communication systems, we refer to the opposition of the cable as characteristic impedance. The characteristics and impedance of the cable. To some degree, everything opposes the flow of electrical current. A regulated AC or DC power voltage source appears to have an impedance of approximately zero as long as we don't exceed the design parameters of the source. So regulated power supplies mean that normally if I take a battery which is not regulated, as soon as you put a load across the battery, the output voltage drops. Now, what makes the output voltage of the battery drop? If V is equal to I times R, and I take a 100 ohm resistor and put it across there, and I start off with 1.6 volts, and as soon as I put that resistor across that battery, the output of the battery drops. You can see that on your car. Go out there and don't crank your car. Take your voltmeter and put it out there so you can see it, and turn on the headlights. As soon as you turn on the headlights, the output voltage of the battery will drop. What's causing the output voltage of the battery to drop? The load sees a voltage. It's not what's causing it. It's the internal resistance of the battery. So every battery has an internal resistance, which means if you load it, its output is going to drop because of the internal resistance of the battery. As soon as you have I, when that I flows through the battery, if there's a resistance in the battery, then the voltage will drop. Where does that voltage drop appear? Well, when I measure across the battery, right? That's what we're doing. So a battery or an unregulated voltage source has an equivalent circuit of this. So we draw batteries like this, but in actuality, this is what a battery looks like, just like that. Looks just like that. So that means if I put current flow through my circuit, so as soon as I come over here and put that right there, I have current flow, right? As soon as I have current flow, then that battery, that resistor inside the battery is going to drop a voltage. Now, if I come up here and pump more energy into it to compensate for that voltage drop, then that's what we call a voltage regulator. So that's what a voltage regulator does. So when you crank your car engine up and you look across there, it's going to go up to over 14 volts, and you're going to turn on the lights now, and the output's not going to drop. So even though the alternator has an internal resistance, we got a regulator that looks at the output. And if the output tries to drop down, what does it do? It puts more energy into it. Does that make sense? So regulated voltage sources appear to have zero impedance, but they don't. They have impedance. It's just there's a circuit that compensates for that, right? You understand? And as long as you stay within the design parameters of the alternator, then the output will not drop. But you go out there and get a piece of 4-aught wire and put it across your battery, by George, the output of the alternator is going to drop down because you've exceeded the what energy we can put in there, right? Does that make sense? But when we get into every AC or DC signal source, we'll have an internal resistance or internal impedance. So it means when I load these guys, the voltage is going to drop. Does that understand? Because of the internal resistance of the signal source. An internal impedance causes the voltage provided by the source to drop when the load is attached. Power is work. Everybody understands that. It is not voltage. It is current. And it's not current. It's both of them. So power is equal to V times I, right? You understand that. So it's not just the voltage. It's not just the current. Your house has two voltages available in it. It has what we call 120 and 240. But you don't pay a 240 bill at the end of the month. You don't pay a 120 volt bill at the month. You pay a power bill because they're not charging you for the voltage. They're not charging you for current. They're charging you for the work that's being performed by their power, right? Does that make sense? We don't call it a voltage company. We don't call it a current company. We call it a power company because that's what they're selling. They're selling power. Now, you can't have power without voltage, and you can't have power without current, right? You understand? The primary goal of a communication channel is to get the maximum power transfer between the source, which is the transmitter of the signal, and the load, which is the receival of the signal we're trying to drive. Everybody understand that? Impedance matching. The power transfer between the transmitter and receiver in a circuit is maximum when the impedance in the circuits match. And we'll show that in a minute using resistor. We're very familiar with Ohm's law. Every signal transmitter has impedance. This is what causes the output of the voltage to drop the signal. So we can't do anything about the drop in signal. So since we know we're going to get a drop in signal because of the resistance of the signal source, right? You understand? We're going to figure out how to get the maximum power out of the signal drop. In the example on the next slide, we're going to use resistance with an internal. We're going to use a source, a signal source that has an internal resistance of 100 ohms, and we're going to use R. We're going to use resistor. And what we're going to do is we're going to change the resistance from a 10 ohm to 100 ohm to 1K. Which of the following, when I load this thing down, I'm going to put a 10 ohm resistor on a signal source that has 100 ohms worth of resistance. I'm going to put 100 ohms on it, and I'm going to load it with 1K ohm. Which one will produce the most power in the load? So these are going to be the loads. What do you think, Slee? Say something. Dan, what do you think, James? Say something. I don't know what you mean the same. Pick one. Tell me which one you think. 1K. What do you think? 100. What do you think, Ivan? Huh? The smallest resistor you think is going to produce the most power in the resistor. Okay. So here's what we got right here. We got a signal source, and we're talking about AC. Right? You understand? I could put a DC up here, but this is AC. And so we're saying, okay, I've got a 10 volt source. It has an internal resistance of 100 ohms. So this is a signal source equivalent circuit that we're looking at here. And I'm going to come up here and load this with 100 ohms. So what we're going to do is we're going to calculate the power getting to the 100 ohm resistor. Now here it's best to use what we call the voltage divider formula. Can y'all add those together in your head? So what's 100 plus 10? Okay, so the voltage divider formula says we can take the ratio of the resistor to total resistance. So that would be 10 divided by 110. We multiply that times the source, and that'll give us the voltage drop across the resistor. We can do this extremely fast. We call this the voltage divider formula. If you hadn't heard about it, this is really cool because I don't have to calculate current. And we're going to find out it's going to be real easy to calculate RT. So the voltage divider formula says the voltage drop across a resistor in a series circuit is equal to that resistor divided by the total resistance in the circuit times the voltage. Okay. Then, since we got the voltage and we got the resistance, the power formula that we probably use is V squared over R. So we're not trying to calculate the total power in the circuit. We're trying to calculate the total power across the 10 ohm resistor. So that means with a 10 ohm resistor, I get 82 milliwatts. Did everybody do that and get that? You don't need to do it. And this is why knowing those other watt law formula will save you a lot of time. The voltage divider formula for series circuits. This is the best way to do it because here you don't have to calculate I. So everybody get 82 milliwatts. Now I could vary this 1 ohm at a time, but we're going to jump in 3 just to know exactly what's going on. So 82 milliwatts, is that the right answer? Okay, so what we're going to do next? We're going to pop the 10 ohm out and put 100 ohms in. Uh-oh. don't know what's going on with my slides. So 100 ohm resistor, we take 100 divided by 200. So now my total resistance in the circuit is 200, right? Y'all understand? So the voltage drop across that resistor, of course, y'all know this from Ohm's law. They're the same size, they're going to drop the same voltage, right? So this is going to be 100 divided by 200, or 1/2 divided by 10 times 10. That's 5 volts. 5 squared over the resistor itself is 250 milliwatts. So if you chose 10 ohms, you're wrong, right? Y'all understand that? So with 100 ohm, I get 250 milliwatts to the load. Now notice it here. The internal resistance of the source is matching the internal resistance of the load, or the actual resistance of the load. So if you chose, now let's go to 1K, if I can get this to advance right. Yep. Okay, so here's 100K. Here's 1,000 ohms. 1K. So at 10 ohms, we had 82 milliwatts. At 100 ohms, we had 250 milliwatts. And so we do our calculation. So now my total resistance of my circuit is 1,100 ohms. 1,000 divided by 1,100 ohms times 10 is 9.09 volts. But when I take 9.09 volts, or 9.1 volts, square it, and divide it by 1,000, we're back to 82.6 milliwatts. Now you could do this in 1 ohm, you could do it in tenths of ohms, you could do it in 1,000 ohm, thousandths of an ohm. You will find out that you get the maximum power transfer to the load when the opposition of the load matches the internal opposition of the source. And we call this impedance matching. Is that cool? A lot of people will get that wrong. I mean, most of the time they'll choose the smallest resistor. They say the smallest resistor conducts the most current, right? You understand? Well, even in a series circuit, the smallest resistor produces the less power because current is constant, right? You understand that? Normally in a series circuit, the biggest resistor produces the most power, but what we're not considering when y'all gave y'all's answer was the internal resistance of the load. That makes sense? Maximum power transfers occurs when we have impedance matching, which would be the 10 ohm resistor. And I don't know what it's doing. I need to go back and check and see what's going on here. I think it's going through the whole thing again. So in a communication system or a channel, every signal source we know has a what? Internal impedance. Every conductor has an impedance. Every load or receiver has an impedance. But when is the power transfer to the load the maximum? When all the impedances in the channel do what? Match. Now you got to understand, instead of this being arbitrary, if I'm going to get impedance matching, then I've got to set the impedance of everything in the circuit. I've got to know the impedance of the source. I got to know the impedance of the load. I got to know the impedance of the cable. So instead of this being an arbitrary value, what we do is we set these impedances. We design the cable to give us a certain impedance. We design the transmitter to give us a certain internal impedance. We design the load to give us an internal impedance. And if all the impedances in the channel match, we get what? We get maximum power transfer to the load. The two primary types of cables we use is what we call twisted pair cable. Now, when I look at a twisted pair cable, I see an inductor and I see a capacitor. An inductor is something that's a conductor that's rolled, right? You understand. And a capacitor is when I have two conductors separated by an insulator. So notice here we have the rolling of the conductor, the twist of the conductor gives me an inductor, right? You understand. And then the distance between the two gives me a what? Capacitor. And then the resistance of the wire itself gives me R. Now this is going to set up what we call an impedance, right? You'll understand that. So now we have those formulas that come into play, and we're looking at what we call resonant frequency. Now these inductors and these capacitors only come into play when you put AC on this thing. And that's what signals are, right? You understand signals are AC. So I'm trying to send data over these communication cables, and my ones and zeros are doing like this. So that's going to be an AC signal, right? It's going to be alternating current. Coaxial cable, which is one we use, and you run into this all the time. This is what they use in your cable TV, or if you have a direct TV and they put that antenna up on your house, they don't run regular wire down to your TV. They run coaxial cable. So the impedance of the antenna is your source. It's got a set impedance, right? You understand. The cable has a set impedance, and when you screw that sucker in the back of the TV, that input to your TV has a set impedance. So can you see the coax cable? So I have an internal resistance right here. I have an insulator. I have an outside conductor, and that sets up a what? Capacitor. The looping in the shield basically sets up inductors. So this is basically what we refer to as a tuned circuit. But that impedance will only occur at a certain what? So X of L, which we'd be talking about the inductors, is equal to 2 pi FL. So this is going to be at a certain what? Frequency. The X of C, which is the opposition that these capacitors represent, is 1 over 2 pi FC. So there it is right there. So these cables are rated at a frequency. A lot of coax cable is rated at 100 megahertz, and this is rated at, 10 megahertz. This guy's rated at 100 megahertz. So that's what we send information on. We send it on a carrier at that speed. So if I come up here and take my ohm meter and I put it between here and here, what's it going to measure? If I don't have the cable hooked to anything, it's going to measure infinite ohms, because my calculator, my ohm meter does not measure impedance. It measures resistance, right? You understand that? But if I was to load this cable down and I was to look at the voltage drop across the cable unloaded, and then I was to load it down and I looked at that voltage drop, right, we could see what's going on. Everybody okay? So when do we have maximum transfer in a communication channel? When all the impedances in the channel do what? Match. And we refer to that as, so when we say this is a 100 ohm cable, but that's what we refer to as the characteristic impedance. And this right here is either 75 ohm cable, is what we used to use for networking, which was RG59. I get these all, and then your TV uses RG58, which is 50 ohm cable. I think I told you about my father-in-law, right? Pulling that big truck to his backyard and broke his coax cable. And what did he do? He went out there and twisted it back together and wrapped tape around it. And his TV picture was crummy after that. And why? Because what did he screw up? He screwed up the impedance matching of the cable. So that means when we splice these things or terminate these things, we're really going to have to follow some guidelines to maintain the twist in the cable, to maintain the spacing between these two conductors, right? We got to maintain those spacing. So coax cable, we just can't do what? We just can't splice it together. We have to come back and do that. I got these out of, and this is DC. So if you put DC on the twisted pair cable, it has, all it's got is R, right? You understand? And what determines the R of a conductor? The material it's made out of, the size, the length, and the temperature. What determines the reactance of a cable is this X of C and X of L, right? What determines the impedance of a cable is X of C, X of L, and R. Now you'll find out that a lot of people in AC use the term impedance to even represent R. I guess because it just sounds cool. That means when we splice these cables, these communication cables, we got to consider the impedance of the cable. So on twisted pair cable, we can only untwist those things a certain distance. So we got to really maintain that, right? You understand that? In coaxial cable, normally coaxial cable, we put two coax connectors on there, and I'll show y'all. And then we have a little tube splice that we snap the connectors in to splice them. I don't know if I put the characteristic impedance of these cables, but I should. So in twisted pair cable, we have two types. We have what we call UTP. UTP stands for unshielded twisted pair. And then we have STP, which I don't think this book covered, which stands for shielded twisted pair. What advantage would shielded twisted pair have over unshielded twisted pair? So we have what we call UTP. And then we have what STP, and that's not the lubrication, or the added STP is the rest of the edge over the next part. So what does UTP stand for? Unshielded twisted pair. You know what does STP stand for? Okay. Y'all know what a shield is. In conductors. I think we talked about that before. I'm almost sure we did. This is what we consider to be a shield. Well, basically they use a combination of both. Of course, you see that the braid is in contact with the foil, so both of them consist of a shield. Foil makes it more flexible, but it has very little strength. Braid, we have a lot of gaps in it, but it adds strength, right? You understand? So usually they use a combination of both. And the braid is in constant contact with the shield. I mean, with the foil. It could be foil. When we look at that high voltage wire, they have a shield. It's copper and it's foil, but it's thick enough in itself to add mechanical strength. I did say that, right? Okay. So this is the shield on this medium voltage cable. And I didn't start my camera up, sorry. I need to start doing that. But so this is a cable. And of course here's the shield right here. This is solid copper. So you can imagine this stuff, this takes a lot of money. In fact, the conductor itself is copper. But this is the shield. So what is the function of the shield? Well, here it has a different thing, but normally what a shield is in there for is to prevent what we call EMI. You know what EMI is? Yeah, electromagnetic interference. So communication cables are trying to broadcast all the time. And of course, they are conductors, so they're trying to receive electromagnetic interference. So what we use shields for is to reduce the amount of EMI being radiated and reduce the amount of radiated energy getting into the system. And that's the function of the shield. On high voltage cables, it's in there to equalize the stress on the insulator. So what we have is we have the shield out there, and it puts equal stress all the way around the insulator. So STP cable would be less immune to electromagnetic interference. STP cable would be less immune to it, but it's going to be a lot cheaper. Makes sense? The predominant in networking is UTP. So all these gray wires, all these white wires you see up there, this is UTP cable, twisted pair cable. And so when we terminate, that's what we're going to have to learn how to terminate. So we're going to terminate some UTP cable. Cat5. The category determines the operating frequency of the cable. So Cat5 cable is rated at 100 megahertz. I think Cat3 cable, which is what we first started off with, was rated at 10 megahertz. So that means if you run all this Cat3 cable in your network and you go up to 100 megabit network, you can't run 100 megahertz on Cat3. So we have some portions of our college that's still running on a 10 megahertz network, because if they didn't run it at 10, then what would happen? They'd have to go back and change all that cable in the whole college over to Cat5. So these are bending radiuses. So here we're very, very concerned with the bending radius. And why is that? This is coaxial cable, by the way. This is RG58. Now this is RG58. Coaxial cable. So this is Pitheon cable. You can't match, or you can't put RG58 and RG59 in the same circuit. So that means you just can't go out and buy coax cable if you need something, right? You got to make sure you buy the right cable that matches the impedance of the system that you're going to put in there. Why do we have to really, really honor the bending radius on these communication cables? Well, if you mess up the spacing between the wires or anything like that, you've changed the characteristics and impedance of the cable. So multi-pair UTP, we need to 10-inch diameter on your radius, or bending radius. So if it's 10-inch in diameter, if it's 4-inch diameter, well, we need to maintain a bending radius of greater 1 inch or greater, right? And fiber, we'll look at fiber in a minute. Zip cord, that's what we're using, and we really, really have to honor these bending radiuses on these cables. Some of them you got no option. This is a telephone twisted pair cable, and you can't even see the bending radius of this one. This is that telephone cable that you see. This is twisted pair cable, and it's shielded. I'm going to see the shield. Put it on the camera. And then that's twisted pair cable. I'll take a 2-minute break and let me pull out some of this stuff. So this right here is a coax cable stripper, because the trick is to not cut the insulation. Not scribe the center conductor, right? So the trick is not to scribe the center conductor. This is this guy right here. Oops. And it's to cut through the insulation, to not scribe the shield here, but to cut it out here, right? Which is pretty interesting. Let me get this right here. So the trick when you strip it is to not scribe the center, or not cut strands on the center. You need to cut through the shield. Through the insulator right here. You need to cut the shield with the insulator, and you need to come in and cut off the outside jacket without scribing the shield. So we have these special little stripping tools like this. This one works with RG59, it works with RG6 and RG9. Once you get it adjusted, and what you do is you push this little slug out right here and move it to a different size. So right now we have it set for 8, so that's RG58. Then what you have is you have this little Allen head screw wrench here, where you actually adjust the depth of the two blades. And so that's what you do. They can't know exactly what's going to go on. So what you do is you get a sample cable and you start playing around with it so it strips it correctly. These are called cable cutters, and you have different cable cutters for different diameter wires. So when you cut these things, you want to try to cut them with a knife or something like that. And to cut it to the right length for termination or splicing, it's got a little plateau right here. I'll pat this around, let y'all play around with it. And what we do is we open it up, push down right here. We lay it on there until the tip of the cable lines up with the tip of the little plateau right here. Put our finger in the little groove, spin it around, pull it off, and then it strips the cable. So if you're going to work with coax, so if you've ever been in there where the guy's doing work on your TV, of course, he has something like this that gives him the ability to strip that coax cable correctly, right? By the way, if y'all play around with it, make sure you clean up your residue. Oh, I had one down here. This is a stripper for twisted pair networking cable. And what you do on this one is you adjust the depth of this screw right here. Here's your blades. We'll look at these later on. These are different blades that we use to strip. So on twisted pair cable, you need to set the depth of the blades so it don't scribe the wires, right? That makes sense? And then of course we come in and just lay it in and do the same thing, just spin it around, and we pull off the insulation, and then this will be our twisted pair cable. And you can see the actual twisted pairs. And these are standard colors, so later on we'll learn the actual color code that we use. And I untwist it. And some of the things we can't do, right? We can't untwist these a certain distance, because if we do, we change the impedance of the cable. I've seen people run network cables, and they just pull out the twist. They'll cut off about 4 or 5 inches, and they untwist it because it makes it real easy to put it in the connectors. But then they screwed up the speed of their network. So networks understand that, and what they'll do is they check communication. If it don't work at a certain speed, what do? They automatically go back to the next lower standard speed. You know, so you might have 100 megabit switches and everything in your network, but if somebody don't terminate the cables correctly, your network might still be running back at 10 megahertz, right? This is Cat 5 Cat5, Cat3. So that's something you got to really know when you look at the interval. If you look real close, you would notice that the twisting of the pairs for Cat5 is different than the twisting of the pairs for Cat3. The twists are actually closer together to set the characteristic impedance of the cable. And of course, why we got to honor the bending radiuses on these communication cables, if we bend them too much, we're going to change the characteristic impedance of the cable. Does that make sense? And of course, terminating them and splicing them are very, very critical. This is some generic pulling torques for some of these cables. 22 gauge copper wire, solid or stranded. Solid, we need a maximum load of 2 pounds, right? This would be what? 2.2. We need to avoid deforming cables and mounting hardware. Y'all understand why? Well, no, we change the characteristics impedance of the cable. So if I take a clamp and I clamp it down too hard, it causes those wires to spread out. Y'all know when we take something and we crimp it, it has a tendency to make them change out. It changes the gauge. So we don't clamp these things down real hard, right, like we would do like house wiring and stuff like that, where they use those cable nails, where they nail it down nice and firm. Here we don't do that, right? You understand that? Keep communication cables away from electromagnetic interference sources, because if you run them next to something that generates a lot of electromagnetic interference, you're going to pick it up in the cable, right? Keep conduit fields to 50% or lower. And this is in the National Electrical Code. I've been in the conduit where they have that stuff just crammed tight as they can get those cables in there. And the problem is you got all these cables, right? You understand they're all trying to emit electromagnetic interference, and they're trying to receive electromagnetic interference. And now you got them all crammed in a conduit so they can't dissipate heat, right? You understand that? So if you take commercial wiring, where we really start dealing with conduit, one of the things that you have to calculate is the fill. How many different gauge conductors you can put into a conduit and not fill it over what? 50%. So conduit shouldn't be filled over 50%. And avoid splices. So normally when we pull communication cables, a lot of times we waste a bunch of cables. You know, we make sure we have enough pull to go from where we want to start from to where we want to go. And then they keep, you'll see spools laid around all over the place where they don't try to use one spool until it's empty, right? You understand? They try to use one spool, and then if that spool won't make this run, then they get a new spool. But they hold on to the other spool to make a shorter run, right? You understand? Now, we don't like splicing these communication cables because it's real hard to keep a characteristic impedance through a splice. This is recommended separation from high voltage power sources and communication cables. And we use a lot of unshielded cables. Now, and what has really brought about the change of unshielded cables is a type of interface that we refer to as differential interface. And so USB is differential interface. Most of our unshielded conductors are what we call a differential interface. I don't know what happened to my inserted. So the way we used to send signals for years is we ended what we call single-ended interface, where we used two conductors, and then one of them we considered to be the common or ground. Now, what was happening when an electromagnetic wave would come through this thing, it would induce a voltage, a spike into this wire, but it couldn't induce a voltage into this one if it was relative to ground. Does that make sense? So what they did is they figured out an interface that has no common. It didn't use ground. And we use special amplifiers that we call differential amplifiers. And what we do is we send the signal non-inverted. So this would be the actual signal. And then the lead label minus is not negative, it's inverted, right? Does that make sense? So a lot of times we use the plus and minus to indicate other things besides the sign. So that means if I was sending a digital signal up here like this, then on this conductor it would look like this. It would be exactly the same signal, but it would be inverted. And so that way I don't need a common because we always have a difference of potential between the two wires. Does that make sense? Well, we don't use a common. What a differential amplifier amplifies, it amplifies signals that are different. It don't amplify signals that are the same. So what happens, since I'm not using a common, if these are twisted pair of wires, they're right there together. If a magnetic interference comes through this thing, it's going to put a little spike there and it's going to put a little spike there. But now those signals are moving in the same direction, right? You understand? We call these common mode signals. A differential amplifier will reject common mode signals and will pass differential signals. So what would happen on this side right here is I would get the actual true symbol. And what's it going to drop out? It's going to drop out that common mode signal. Differential amplifiers is what has revolutionized communication. So that means I don't have to use shielded wire anymore, right? Y'all understand? Because now the system itself rejects common mode signals. It allows us to use lower voltage levels, so we have almost no current flow at all, which means these guys don't radiate much signals, and it allows us to send these things at real high speeds. So Ethernet uses common mode signaling, USB uses common mode signaling. So if you ever took a USB cable apart and stripped it, you'd see you have 4 wires in there. 2 of them carry power and 2 of them is going to be twisted together. Those are going to be your signal wires. So if you do any splicing or connectors on USB, you need to try to maintain those twists as best you can, right? Does that make sense? And it uses USB, it uses common mode. So now we can send USB signals, you know, a long, long way without having what we call a repeater. Ethernet, we can send it up to 100 meters, which is 330 feet, without worrying about, then we have to send it through some device that either amplifies it or we have to use it before that. So that's why we have these devices called switches and routers and all that kind of stuff. Not only do they allow us to change the path of the signals or specify the path, they also act as what we call repeaters, which means they do what? They take the input signal and they re-amplify it so we can send it 100 meters more. So your predominant networking cables is going to be hardwired cables. Is going to be either Cat5 or Cat3 cables, and they're going to be up to 100 meters before you have to do something, right? That makes sense. And why? Because they use differential signaling. USB is still rated at about 15 feet, even though a lot of people cheat out on that all the time. Some USB cables are shielded. Video cables are supposed to be. So this is how much we, by the way, if you have to take a signal wire, if a signal conductor, cable ever crosses a power cable, you're supposed to cross it at 90 degrees. You're never, ever, ever, ever supposed to parallel a signal conductor with a power conductor. You're never, ever, ever supposed to run a signal conductor in the same conduit as a power conductor, because now you're going to radiate the whole length of the cable. If you run it at 90 degrees, the only problem you're going to have is right there where those things cross that 90 degrees, right? It gets across real. So sometimes you cannot avoid crossing a signal cable with a power cable. But if you ever do it, you need to cross it at what? 90 degrees. Does that make sense? And also, you never want to run those things side by side. You never want to put them in the same conduit. Splicing. Well, of course, we have solder, we have twist on, we have bolt on, we have crimp on, and we have compression. And these are metal splices. These right here we refer to as wire nuts. Have you ever seen these? These are used a lot in the electrical trade. Now, the correct way to do this is to bring all your conductors in. And this is kind of misleading too. We need to probably look those up. They're sized in different colors, but the color does not specify the gauge of the wire. The color specifies how many different gauges you can put into that wire nut. Does that make sense? So this right here might be rated at 8 gauge, but if we look at the box, it says 8 gauge 2 wires. And then it says, then it might say what? Then it might say 12 gauge 10 wires. So when you get these things, the colors does not indicate, it indicates the maximum gauge you can put on there, but the minimum gauge would be determined by how many of those you use, right? So blue can run anything between what? 22 gauge up to 18 gauge, right? You understand? So let's see if we can find this on the internet. I don't have a box in here. Normally when you buy these things, they come in a plastic container, and then on the side of the plastic container, they'll come in and they'll tell you how many gauge wires. We call these wire nuts, by the way. Why we call them nuts? Because on a boat, the thing that, so we have bolts and we have nuts, right? You understand? So your bolt has the thread on the outside threads, and your nut has the inside threads, right? And that same thing true with a wire nut. So you're not supposed to just lay the 2 wires together and put the wire nut on there. You're supposed to twist the wires together, and then you perform threads, and then you put the wire nut on there. The wire nut is intended for insulation. It's not intended as the device that provides the physical strength of the splice. Let's see if we can find like a wire nut chart or sizes, capacity. And these are Ideal. Ideal is a maker of a lot of electrical trade stuff. And if this works out, I'll download it and see if it does. In fact, there might be one in the handout session. I need to look there. It might be something we've already got. Computer circle mills, ampacity, NEC codes, abbreviation, wire nut sizes. Ah, there's one out there. So the gray one, we could put what? We could put 3 number 5s, we could put 2 number 4s, we could put 2 number 3s, we could put 2 number 16s, we could put 1 number 20 with 1 number 4, with 4 number 22s. So you see how this works? So this is up there. So when you look at a wire nut, you can't say, well, that's for 12 gauge wire. You might say that would be the maximum gauges you could put in there, right? You understand? But what we're looking at is how many different gauges that wire nut represents. And this chart is up there on the web for you. This is a good chart to look at. So a blue one would hold all these different things. We're going to be using yellow ones. So let's see what we're going to do with yellow. Let's see what yellow will do. So yellow is rated at, they're also rated on the voltage, right? You understand, because they're insulators. So yellow is rated at what? 600 volts. What can we put in there? We could put two number 14s. We could put two number 12s. We could put two to 4. I'm sorry. We could put 2 to 3 number 14s. We could put 2 number 12s. We could put 2 number 7s. We could put 3 number 5s. I'm sorry. I'm reading this. I need to look at my thing. We could put 4 to 5. I'm reading it wrong. So on our yellow one, let me find it again. We're going to be using yellow. So we could put 4 to 5 number 22s. We could put 3 to 5 number 20s. We could put 2 to 7 number 18s. We could use 2 to 4 number 16s, 2 to 3 number 14s, 2 number 12s. You're going to see this guy used a lot in residential wiring. The two primary wire sizes we use is number 2 and number 12. On a 24 volt circuit, we usually use number 12s. On a 15 amp circuit, we use 14. On a 20 amp circuit, we use number 12s. On a 15 amp circuit, we use number. But if you needed to twist more together, then you might go to a different size wire nut, right? You understand? So if we come over here and look at gray. No, this is not as big. I thought gray was bigger. I know orange is bigger. Does that show orange? No, this says 2 number 14s also. But what you could do if you needed to run 3 number 14s, then you could use yellow. If you needed to run more, then you would use a different wire nut, right? Does that make sense? And these are made for splicing. And what you do is you twist the wires together. You twist the wires together clockwise. And then you do what? Then you put the wire nut on top of the twisted wires. And then a lot of people will put a piece of electrician tape around the bottom in the direction that the wire nut twists. And that way it prevents the wire nut from backing off, which is a practice that we'll probably use. Let me go. We need to go to the lab today. So on this slide, these are kind of arbitrary values because what determines what gauge wire you use is how many of them you're going to use, right? Does that make sense? These are what we call pressure splices. We use these a lot with stranded wire. Stranded wire is hard to splice because it wants to do what? When you twist it together, it wants to birdcage, right? But if we put it in a compression place where the wire's got nowhere to go, then we use a lot of compression splices on stranded wire. A lot of them. Can you see how they work? This is very popular. So we put our wires on top of each other, and then what do? Yeah, we screw the nut down. This one, we have 2 that we put in. We put the wires where they won't splice together inside here and torque it down. I haven't seen this one before. This guy right here is used a lot in terminal boards. You'd have to look inside the terminal board and actually see it, but it's used a lot. So y'all can see what these boat pressure splices look like. You'll see how they work. Have any problems with that? Works really, really well with both stranded and solid strand wire. These are compression also. We call these crimp splices. Some of them don't have insulation on them, some of them do. These weren't really stranded and solid strand wire. By the way, this little thing comes from Harbor Freight, I believe. And of course, they have different colors. What does the color tell you? They give you the wires you can use to splice, right? By the way, those splices are different than wire nuts. And you see a ton of these. Because we don't have to solder them, they're crimped. So what does that mean? Well, that means we're going to put the conductors inside these splices, and then we're going to use the crimp tool to crimp it down onto the conductor and also on the insulation. So normally what you have to do is you have to crimp these twice. You crimp one on the inside for the conductor, and you crimp one toward the outside to crimp down on the insulator, right? Does that make sense? And these guys, we use tons of this. This is a compression connector. This works kind of like a crimp splice. These guys don't usually have insulation. Guys, I just had it. Let me show you all. Oh, here it is. What I like this for is this is aluminum. What problem does aluminum have? Besides having a higher resistance, what problem does it have? Yeah, oxidizes real bad. So anytime we want to use aluminum, we have to use an antioxidant. We're supposed to use, and we don't have to, but we're supposed to use an antioxidant agent. So this came from actually a chunk of Alabama Power, I think, wire. So this is a compression splice right here that's been compressed around the two wires, and you can actually see the oxidation compound in here. It looks like grease. But don't use grease. You need to actually use that antioxidant compound. And of course, you can see these pop things on the wire. I'll get that on the photo. So they even sell that stuff at Lowe's. I mean, so if you're dealing with aluminum wire is okay to use. It's just that anytime anything that you have not necessarily exposed to the environment, anything inside the terminal, inside the splice, you need to make sure that you put that antioxidant agent all over the wire. Coat them really good. Now copper, we don't worry about that. We do this on copper too, but anytime you mix, and also make sure if you mix aluminum and copper that you put that stuff on there too. Anytime you splice aluminum, anytime you use aluminum wire and you splice it to something or you terminate it somewhere, you need to make sure you do what? If you terminate it with these crimp things, you need to make sure you put that antioxidant. Now, the problem we have with high voltage cable is what? Well, high voltage cable consists of all types of layers. And what they're trying to do, of course, is they're trying to keep all that high voltage in, right? Does that make sense? High voltage has a tendency to create ozone. Now, the problem with ozone is it breaks down most insulating materials. So what we do on high voltage and medium voltage cable is they surround the
Hello, and welcome to 3M. We're the innovation and practical solutions company you have come to trust for over 100 years. You'll find innovation and practicality in everything we do, including our solutions for medium voltage splicing and terminating. This is an interactive module, so please click the arrow below to begin. This presentation contains examples for general practices only. For specifics on individual applications, see the 3M datasheets and technical illustrations. It is the responsibility for the users to test and verify the purpose of this module is to familiarize you with medium voltage cable voltage applications. Then, we'll take a look at the 6 layers of medium voltage cable. By the end of this module, you should be able to describe the function of the 6 layers of medium voltage cable. Medium voltage cable is electrical cable with a voltage rating of 2 kilovolts to 46 kilovolts. Any cable with a voltage rating higher than 40...
When we start talking about high voltage and low voltage, the voltage level depends on the application. In housing, we call 240 high voltage and we call 120 low voltage. When we start dealing with cables and transmission, then low voltage is usually considered anything below 2,000 volts. And then medium voltage is from 2001 volts up to what did he say?
6 kilovolts, such as 69 kilovolts, is considered high voltage cable.
So anything up to 6
Medium voltage cable is what is commonly used throughout electrical distribution systems, power plants, and industrial facilities, such as oil and gas production facilities. It is also what is used to bring power to our neighborhoods, schools, malls, and offices. There are 6 distinct layers in medium voltage cable. They are conductor, strand shield, insulation, semiconducting layer, metallic shield, and jacket. Each of these layers are critical to the cable system. You can click Next to continue, or click on a specific layer to jump to an explanation.
You can't do that.
There are 2 basic types of medium voltage cable, single conductor and 3-conductor cable. Single conductor cable consists of 1 conductor per cable, while 3-conductor cable has 3 individually insulated and shielded conductors. The conductor is the heart of the cable, as this is the portion of the cable whose sole purpose is to carry current. The strands that make up the conductor can be made of either copper or aluminum. Copper is generally used for industrial applications, whereas aluminum is generally used for utility applications. Conductor configurations are concentric, compressed, compact, or solid. The next component is the strand shield layer of the cable. This is a semiconductive layer of the cable. Its function is to shield the cable insulation from any air that may be surrounding the conductor strands. Without this protective semiconductive layer, the air will ionize, resulting in partial discharges. This can deteriorate the cable insulation to the point of failure of that cable. The purpose of the insulation layer is to contain the voltage of the cable. This layer can be made of materials such as EPR, or ethylene propylene rubber, or XLPE, or cross-linked polyethylene. Insulation has a standard operating temperature rating, as well as an emergency operating temperature rating. The next layer is the semicon layer of the cable. The function of this layer of the cable, somewhat similar to that of the strand shield layer, is to shield the cable insulation from the air that is between the cable insulation and the metallic shield. The metallic shield is the conductive, metallic component of the cable's shielding system. It serves many different functions. It contains the electric field within the cable, provides symmetrical radial distribution of voltage stress in the insulation, limits radio interference, and reduces the hazard of shock. It also serves as a return path in the event of a short circuit, and for concentric neutral cables, it provides a neutral return path. The metallic shield must always be grounded. Shown are common cable types. Tape shield cables fulfill the 6 different functions of a medium voltage cable in 6 different layers.
This is what this
Wire
is.
shield cables have the same basic construction as tape shielded, and is often considered interchangeable with tape shield. Unishield combines the metallic shield, semiconducting layer, and jacket into one layer. This cable is designed to be very compact. Concentric neutral metallic shields also serve the function of a neutral conductor. Jacketed concentric neutral cable is basically the same as concentric neutral, except it has an outer...
We don't need to know. Let's know. So, high voltage cable, when we splice high voltage cable, you have to maintain all the layers, right? Don't understand that. So here's the conductor. Right around there we see a black loop. This is the first semiconductor layer. What's this semiconductor layer in there for? Is everybody sleeping through the video? So what's the first semiconductor? What's the two semiconductor labels for? Well, the problem is when we start dealing with high voltage wants to jump everywhere, right? If it jumps or arcs, it creates what they call a corona or ionization, which creates ozone. Ozone breaks down all insulators. So if they let this cable arc on the inside, this insulator is not going to do any good, right? You understand? This semiconductor layer, what does it do? Well, it prevents a corona from building up between the insulator and the shield. And then we have the shield. What's the function of the shield? The primary function is to equally distribute the stress, the electrical stress inside that conductor is to equally distribute it around the insulator. If we don't do that, then what's going to happen is if it's got any other metal around there, it's going to try to move the magnetic field toward that metal. So all your voltage will be trying to be held in by one side of the insulator. That makes sense? So the primary function of the shield is to equally distribute the what? Equally distribute the stress around the insulator. Plus it prevents the cable from generating a lot of electromagnetic interference too. But the primary function is so we can lay this thing across any metal and it won't cause any problems. But when we terminate this, or when we terminate it, or when we splice it, we got to maintain all those layers. Does that make sense? We got to maintain the semiconductor layer. We got to maintain the insulator layer. We got to maintain the second semiconductor layer. We got to maintain the shield, right? You'll understand that. If we don't do that, then what happens? Then the cables break down. And you don't want these suckers to break down. What did he say? 2,000 volts push up to almost 7,000. We'll look. They rate these things different. I always heard 10,000 volts or medium voltage. And then high voltage was 10,000 volts up to something. And then we have what we call ultra high voltage. And then we have very high voltage. We have very high voltage and then we have ultra high voltage. We're getting at some of these cables coming down from, on these high transmission lines, we're looking at 700,000-800,000 volts. Of course, those don't use insulate. They use air for insulation. So what we have to do to splice these things is we can't just splice them. We have to buy what we call splicing kits. So we can't splice these things. They cost so much money.
EM Standard Cultural Tape Electrode Joint offers a viable cost-based alternative to heat shrink cable jointing technology and allows for a reduction in installation steps. Unlike heat shrink alternatives, a molecular permanent set ensures constant radial pressure is exerted on the cable for the duration of the cable joint's life. Unlike the individual layers that are necessary for a heat shrink joint, which must be allowed to cool sufficiently before the
3 outputs are what they call a cold joint.
Splice bodies contain all the necessary layers in one component. Any additional cold shrink layers, such as our outer protection tube, can be applied immediately. Scott's 13 semiconductor is used to overtake the connector. Layers are applied tightly around the connector, overlapping the primary insulation on each side. This stage replaces the need for a heat shrink tube used in competitive heat.
So now he's splicing the conductor.
3M
Right?
invented cold shrink technology over 30 years ago. Our cold applied products utilize the unique cold shrink delivery system designed to make cable jointing, insulating, termination, and abandonment as simple as possible. Compared to heat shrink alternatives, there is less chance of damaging XLPE cables, less room for joint to error, and no cooling time needed before energizing. It is easier to
Well,
use
this is
in
heat
closed
shrink.
areas,
You see him replacing
and
all
there
the
is no
layers. The guy on the
requirement
top's
to
using
stop
heat
site
shrink. The guy on the bottom's using what they call cold
time-saving
shrink,
benefits
which is
of
pretty
cold shrink
neat.
can be
So
considered.
it's got
Thus
a
lowering the overall
Teflon thing
installation.
holding it apart, and all he's doing is pulling it out.
Additionally,
It's
many of the joint problems are comprehensively
So this is
tested
heat shrink.
before
You
release.
see, it's got up here at the
Something
top, have to
simply
shrink it
not
down.
possible with heat shrink due to its material nature. Finally, as a result of continuous development and refinement, only 3M can offer you such choice in cold shrink technology in terms of product cost and flexibility in its application.
So you see, here's the shield. This guy's replacing the shield. So you see the metal tape they have here. That's actually a spring. So this guy at the top, he's replacing the shield. You know, see that? Can you see how the cold shrink runs? This is what's on this cable right here, by the way, the cold shrink. Oh, he's doing the shield now. So the guy on the bottom is finished. The guy on the top is having the. So the only difference really is one of them uses cold shrink and the other one uses heat shrink. That makes sense. 3M, of course, this is a 3M commercial. They sell the cold shrink. So these guys right here, you just don't splice together. You have to do what? What do you have to do? Huh? Yeah, you have to replace every layer. So you have to place that center semiconductor layer. You have to come in and put the insulating layer. You have to do the second semiconductor layer. Then you have to put the shield, right? You understand? And you're right, it takes a lot to do. That's why we can't do termination or splicing of these high voltage cables. Termination is also a lot to do with that. So this is the actual cold shrink right here, which is pretty neat. So this is a 3M splice right here that they're doing, or termination, excuse me. So you can see this stuff right here is very flexible. You can actually see where they've put some putty in here to prevent corona. And then of course here's the shield. And we have to bring the shield out, so that's what this braided, we call these pigtails, by the way, that's what the pigtail is. So this right here would actually what would be connected to ground, right? Does that make sense? When you terminate it. So you have to connect this to ground when you terminate it. But this has been pulled back. And this, by the way, they had to cut this off. And they gave it to us because it's not something in here they did wrong. So this wasn't terminated correctly. So what did they have to do? They had to cut it off and redo it again. And you're talking about, for a splicing kit, you're talking about a few $100s. So we don't want to make many mistakes with these. I can't remember who actually gave this to us, but as you can see where they actually cut it off here with a big cable cutter. We actually trimmed this back right here so we could actually see the different layers. So this is the medium voltage cable termination. Now, if you can do those right, then you make pretty good money at that. That's where we're at, so we can go ahead and go to the lab. So this slide that I gave y'all out, it shows you the actual compression tools. Y'all okay on that? So we showed y'all one that was actually compressed. And then this shows you how all these guys would be spliced and terminated. Then looks like we're going to have to go one more class. And then we'll get into the ones that we're going to do lab on. So the different types of terminals which I handed out, the different types of crimp tools, and also we'll get into how to terminate terminal blocks. We'll look at those, and then of course we're going to do some UTP cable for Ethernet applications, and let y'all see how to do that. I'll talk about punch down box, punch down tools. Y'all be able to do that. So what we'll do Monday is we'll finish this up. What we're going to do the rest of the class is we're going to let y'all finish up your soldering lab. Okay? I'm going to try to finish up your soldering lab. Let's go lab. All the stuff, by the way, is on that cart right there. So y'all might have to dig some stuff out. So we kind of did pack it really good. But your unfinished, the ones you were working on, should still be in that unfinished in the box, right?